Hello everyone, it's October 2nd. I'm back. Alright, let's do this. Minimum time to make rope colorful. That seems to be a new problem. I never seen this one before. Alice, well, maybe I did. Alice has n balloons arranged on a rope. You're given a zero index string colors, where colors I is the color of the ith balloon. Alice wants the rope to be colorful, okay? Does not want two consecutive balloons of the same color, so she asks Bob for help. Bob can remove some balloons from the rope to make it colorful. You are given a zero-index integer array, needed time, where needed time I is the time in seconds that Bob needs to remove the ith balloon from the rope. Got it. Return the minimum time Bob needs to make the rope colorful. For example, in this, you just need to remove minimum time. So I can remove this, which takes 3 seconds, or, so what we want is just no two consecutive balloons of the same color. So we can remove everything, all right? But there's always, this will be 0. This will be 1 and 2, right? Which is 2 seconds. Okay. Let's see. We have these balloons. We have a blue, a red, a blue, and a green, right? We want to know, and each time when we remove, they have a different time. What's the min? 10 to the 5th. Yeah, it doesn't really matter the color or not color. It's just a string. We just say we have a string. I want to know what is the minimum number of what are the removal, and also have to be bounded by the needed time to make it no two consecutive is the same. I kind of think you can, like in this case, it's guaranteed that this is the only solution. But I could make this one big and make this one small, so we have to remove this one, right? So it cannot be the first one. Or even I can make, but consecutive needs to be removed no matter what, right? I am thinking. It gotta be a situation that's, it might be easier to remove everybody else. Not this, right? We can say, but if it's not, yeah, that's a good argument. So the goal is to remove consecutives. So why don't we find out where all the consecutives are? Because if you say I don't want to remove consecutives, then there's no way for them to be colorful. So to be colorful, you have to remove consecutive no matter what. Okay, so we have to remove, let's say we have 3. We have multiple. If it's 2, we definitely need to move one of them. Oh, there's no other way. Because I was thinking maybe we can keep them and then remove everybody else. But if we keep them and remove everybody else, if that's more cost effective than remove this, that means remove this is even cheaper, right? So we can just remove this. Therefore, if we're given 2, that's the same. We have to remove one of them, right? And we have more than 2. Let's say we have 3. We have blue, 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 right? If you have blue, blue, blue because you cannot add, all you can do is remove. So you have to remove 2. There's no way, right? You have to remove 2. If you don't remove, well, actually, hold on. If I have 3 consecutive, and on the outside is not the same, then yeah, you have to remove 2. Huh. Are we saying if we have consecutive, they have to be removed until 1 is left? Yeah, because if you have consecutives, which means the color on the outside will not matter because there will always be a difference in the middle. So maybe we can use greedy. So in this case, we do this and then we just remove the find the biggest value and then remove the smallest. Yeah, 1, 2, find the biggest value, remove this. This is not. Find the biggest value, remove this. Prove me wrong. Prove me wrong. That's what I have to say. Yeah, so if you boil down to this, right? If we have multiple colored balloons in a row, they have to be removed until 1 is left. There's no other way. Because if you want to do another way, there's just no other way, right? You have to remove. You have 2 balloons, you have to remove one of them. If you don't, they're not colorful. And to remove one of them, you either remove one of the blues or you remove one of the blues with something else. So if that's the case, I am going to greedy this. Okay, I'm going to greedy this and see if greedy works. If greedy doesn't work, I don't know if greedy works. But how would you do? We just iterate through and then see which are the same. Okay, for I and color, enumerate colors. Actually, no. When I say result equals 0 and current equals needed time 0. And we're gonna go for I in range from 1 to line colors. If colors I is not equal to colors I minus 1, then current equals needed time I. We also need to know how many. So count equals 1, right? So if they're not the same, right? So we have a new thing is not the same as the previous one, then we need to say if count is larger than 1, then res plus equal to current minus, we need to have the maximum as well. Current total, current max. So it'll be current total minus current max, right? We have to do this. And then reset current total, current max, and count back to 1. Else, if they are the same, count plus equal 1, current total plus equal to needed time I, and current max equals maximum current max needed time I. So all this and I'll return rest. This is greedy. Oh, does that mean this week is going to be greedy? I'm not a big fan of greedy. But it is an interesting idea. It's always interesting. 3. ABC, 1, 2, 3. I think I can generate test cases as well for this one. One, 2, 3, 4, 1, 2. Colors needed time. Mean cost. The last one. Oh. I'll do it one more time. If count is larger than 1, res plus equal to. You can say return res plus count larger than 1 multiplied by current total minus current max. Oh, I don't have to, because current total will equal to current max. Yeah, then I don't need count. There's no need for count. Because if it's only 1, then current total will be current same as current max. Interesting. All right, how do we test this? English letters. Okay. Let's go. Yeah, we can run some test cases. Right, from random import randint. Okay, so we need let's do 10 test cases first. Print join rand. So randint char 97 plus randint 0 to 26. Right, this for this in range, let's do length 10. And then print. And also we have to add parentheses. Randint, let's go 1 to 100 for this in range. Oh, it has to be exactly the same. My bad. So L should be rand. L should be 10. Okay. Then we will do 10. We'll do L here, and we'll do L here as well. See doozy. Okay. You know what? There's no repeating. So instead of this, let's just do A, B, C, D. Let's do 4. 0, 1, 2, 3, 4. Nah, 0 to 3. There we go. Now we have repeats. Okay. Try this. Colors must have from A to Z. Wait, what do we have? Oh. I do not know what happened right there. Doesn't seem right. Oh, it is right. And let's be a little bit more bold. How about this? Yeah, let's do this. Hold on. And let's make only 10. That'll make it interesting. Let's see. Okay. I think we got it. Unless we have, okay, edge case. That's the edge case. If this one passes, I'm gonna submit it. Exactly. Okay, submit. It is a new problem, never done before. Ooh, taking a lot of time, but we passed. This is ON. How the heck does ON take so long? What are your good solutions? 2000. I have no clue why this one takes so long. I am doing greedy, right? Greedy supposedly is fast. Yeah, I don't know. But anyway, we got this done. 1578. It's ON. Use greedy. So since we cannot rearrange or add balloons, whenever there are consecutive balloons, they must be removed until only one is left. Right, until one is left. Any other way to achieve this can be proven more costly than simply removing all the consecutive balloons except for one. And we want to use as little time as possible. So the balloon left should be the one that also requires the max time to remove. Yeah, that's that. Okay. We take a look at the solution. Actually, I want to see the submission. see just how other solutions go. 2 pointers. Interesting. What's this mean, 2 pointers? Left or right? Oh, that's the same. Oh, maybe I shouldn't be calling them greedy. I thought it was like greedy. I don't use 2 pointers. I just use 1 pointer. Yeah, you only need 1 pointer. You don't even need to keep the max. Oh, when? Advanced 1 pass. Oh, am I doing the advanced 1 pass? Am I in the advanced group right now? Yeah, I feel like this is my solution. I don't want to do this. I always keep the first one. That's another way to see this. Yes, you can say total time plus minimum. Yeah, you do the minimum of the two. Okay, so this one is done. I think it's it's fitting that we go back to this one. Number of good paths. So we are close, right? The way we do it, we're close. And we failed this test case. Now, this is just difficult to do the test case. Yeah, we failed the last one. I don't know, man. Oh, I think it's right here. Our cat is back. I want to analyze this solution and see what we can do. Oh, I don't know. I don't know, man. I don't think analysis is a good way to go with this. It's just how you gonna analyze this? You know what? I read all 3 hints and this is my solution and it didn't seem to work. I just want a smaller test case. Yeah, I have union find. Feels good to me. This is not right. This should be removed. Previous parent is this. And this shall equal to self.find. Yeah, this we we get a new parent. So this is the new parent. If the current parent, which is path compressed, is not equal to the previous parent, the current parent shall add. The previous parent shall remove. Is this one solve the problem? No. It says key error. Which means it's already been removed. If x in self.group pre-parent, then I remove it. Nope. No, I think I changed it. I changed it into add. Gordy. Oh, I know. I'll submit this and they will give me at least a good test case that I might fail. So I don't have to use this. Oh, that's stupid. I am going to not use this one. I don't know why I say add both previous group and a current group. To me, I think it should be removed, right? You know what? That's my idea, is need to remove it. Because, yeah, I shall remove it. Alright. Let's try. Okay, this is a small enough to deal with. Yeah, that's exactly what I want, because I want to know why it didn't work. Good. Now we can draw. So we have one connect to 0, 0 connect to 2, 3 connect to 2, 4 connect to 2, 5 connect to 3, 6 connect to 3, 7 connect to 6. Good. And the values is 4. No. 4 is 0. 4, 1, 4, 3, 3, 2, 2, 3. 2, 2, 3. Okay, so let's count. It says it should be 10. So 1, 2, 3, 4, 5, 6, 7, 8. So we only have 2 paths. The following 4, 0, 2, that's a path. And 3, 6, 3. It's number 3, 6, 7, that's another path. Yep. How come I only get to 9? Well, let's see. Alright, so we start from 1. And what are we putting out? Parent. Parent set. What's parent set? A set of parent. And dsu.group. Okay, the first one is nothing. And then we go for 2. Right, 2 will connect to 3, so this 2 is also go nothing. Right, 2 will connect to 3, and this 2, so 2 is also nothing. That's correct. But 3, there is something for 3. 3 can connect to 2. Okay, 3 connects to 2, and 3 connects to 2. But this 2, hold on, 3 connects to 2, 3 connects to 2, that's fine, that's the first one. And the second one, 3 connects to 2. So these 3, 0, 1, 2, 3. 5, 7. So they are in one path. That's correct, right? And parent says 5. Do you see the group? Three is an empty set. Oh yeah, 3 is 7. 5 have 2. 3 and 7. For P in parent set. So 5. DSU group, so we have 3 and 7. We found those. That's 2. So that's 1. And I also add len parent set. Why do I add the len parent set? I don't know. Yeah, why do I add the len parent set? I don't think this one's necessary. Yeah. Yeah, it's not there. We don't add len parent set. We should print. Nine. So 4 didn't get anything. 4 didn't get anything. So 4 comes in, right? 4 comes in and connected everything together except for 1. Yes, that's correct. And parent set is 1, understandable. And for P, it's 1 is 0 and 1 is should be 0 and 2. Trouble. Why would 0 comes in? Wait, 0 should come in. Why would 1 come in? Because 1 is always in the group. Because when we set up, I guess, but do we have like a second argument I can pass? I don't think so. No, I don't think so. So you have to check. Nope. Still not right. Now we only have 0. What happened to 2? Group 5 has 2. We solved the one problem, now we still have another problem. They are the same. So 2, 3, 4, their parent is 5. This parent why would it be group 1? Group 1 has hold on, let me think again. These shall all be group 5. So there's some issues with union find. I don't know. Yeah, I feel this should be 5. Yeah, here is still 0. And now we go to 4, right? And then the first 4, we might check 1. And so we union child with node. How about we change this order? Node with child. Yep, let's say node with child, because we say node shall be node with child. And then we have another union. Which one shall go first? Alright, we union node and child, and then the parent will be pointed to node. And child is equal if the two are the same. Parent set dot If they're not the same, and child value is smaller than node value, we go to find the group, right? So these are all the things that child connects to, which what we need to see is if it's next value. So the potential, right? The potential's next value. So if val's potential was not equal to, that's very important. For C in, it's, for whatever the directions, if C is not equal to node, Yes, they cannot be the same. If value C is larger than, it will keep going. Otherwise, we can remove it because we have either handled it or we don't need anymore. So from the adjacency matrix. And value C, so C is, so this one shall be C to potential. Because potential is the one that's smaller. And C is the same as node. So we do that. And then we do this. Now we only have 8. That's ridiculous. That is ridiculous. Yeah, they just don't group together. This is correct. But 3 should have 2 instead of only have 1. I don't understand. So when 3 happens, 3 go to 2. Yeah, like all 4 of them are connected. Three will go to 2, and then they all point to 3, and then 7 and 6, they all point into 3, so these are all correct. And then the union part, I think this part is right. So they all point to C, right? Hold on, let me think again. So we do this and do this. All right, so this is a smaller. Ah, that's why it has to be. I see. Yeah, this has to be belonging to itself. Oh, look at this. Now we pass. Yeah, these actually belong together. In this current round, 0, 2, 3, 4. So we changed a few things. So this has to be still this. And we point them differently. Okay. I mean, this one, I don't even need to say self. Okay, let's see all these. Nice. Oh, I think we got this one. Unless it time out, that's a different situation. Okay, try it. Either run or time out again, right? Doesn't look. All right, I think that's it for the struggle. We're gonna check the solution. It's not that bad anyway. Oh, almost there. So, but anyway, it's not right. All right, let's check the solution. Union find. Nope. You gotta be kidding me. You gotta be kidding me. What? Oh. How do you do union anyway? All right, let's see. Yeah, that's easy to start. Yes. 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 That all the first two intuitions are great. I agree 100%. Oh, hold on. He just did this September 24th, 2022. Oh, yeah, this is one of the contests. This is the last question, actually. You cut by union find. We initialize result. That's true. We union the edges with small values v. Then the nodes of value v on one side can pair up with the nodes of value v on the other side. We union one node into the other by union, and also the count of nodes with value v. We're repeatedly doing union for all edges until we build up the whole tree. I'm just saying, we start from the largest value, okay? And then from the largest value, we can count, and then what? Hold on. Union the edges with small values. Sometimes his explanation I don't understand. Just look. A max value, ij, okay. Count. on this I how many there are. ij is, what is ij? That's the nodes. So we see where they belong. And then we will count the current v. That is true. Ci times Cj. Wait, hold on. How's Ci times Cj? Huh? Again. We go with edges. So v is the largest value. Okay? So v is the largest value. And we have two nodes. So one of the node has its largest value. And we have those two nodes. We have node I and node j. And we find where they belong. Initially, they belong to themselves. And the count. Oh, wait, hold on. What's count? All the nodes. Huh? Okay, let's count. So we go to count to see for the current largest value v, how many nodes are, I guess, is connected to this. Okay, so initially it will be 0 if you are not. And then fj equals fi. So we union these two. So that's like building the tree, right? We union these. So we have the biggest value and then these two, right? So initially is nothing. So we union this. And after we union this, we just say fi is going to be, so we don't really care which one is the parent. I would just call it fi is the parent. So I say this is the parent, and then we go to this parent, and to find out what, so v is going to be, which means this node, okay, this node can connect to v. So next time the next one comes up, next edge comes up, okay, next edge comes up. It doesn't really matter which one is the parent. And next time, if the 2 comes up, and I'll find, well, because when we find, we'll find, because if you belong to the same, if you're connected, you belong to the same group. And if we do union find, they will go to the same parent. They'll point to the same parent. Okay, so now they point to the same parent. So when we have this, group them together, and we know in this group how many this biggest one is. Then So fi is a parent, right? So which means in this parent, we have the largest value is this, and how many we have. So next time, if they belong to the same parent, and on the first round, we all do v, right? We all do the current largest value because we sort it this way. So we get the largest value out, we get a parent, another largest value out, and if one of them, so they will become the same parent, and then here's what we get, the parent and parent. So if they belong to two different parents, then you multiply them together, and then you merge them, and then you update its count. If they belong to the same parent, then one of them will be 0. So don't do it, because after they become the same parent, they must have merged together beforehand, right? And if you do all the edges, if you consider all the edges for the largest value, awesome. If you consider all the edges for the largest value, so this one and this one, let's say they're not all connected. Why do we always rewrite? Because all we know is subtrees. I still didn't understand. If I have two nodes have a parent, okay, and then initial will be 0, and then we say, okay, I'll assign this to the parent, and I'll get the v. Next, we do this. That'll be different. Next time we do this, that'll be different. So those three are separated. They're not connected. So we have 3 parents at the beginning. How? How? This is not working. Let me check. That's a good test case. Because in this case, we can actually print, let's print the edges. This one will first come out, then this one will come out, right? And after this one come out, these two are unioned. Then these two come out, these two are unioned. But when they do this, and then 3 is all gone. That's my question. Right? That's my question. Let's say we're going to print res, print count, and print f. Okay. Oh, you gotta be kidding me. It's from small to large. You said go from the biggest. You said it. Took a look at the biggest value. That's what you said. You misguided me. You misguided me. Let's go from small to large. All right, now it's different. Small to large is different. Okay, if we go small to large, we'll have to rethink. And let's go with the smallest. I don't know. It's sorted. It's so small to big. My God. Okay, hold on. Again. So we go small to large, okay? So we get a bunch of small, and then we build, so union, and a union, and then, so when we reach a V, right, that is the biggest V so far. So each time there's an edge, we union the node. Each time there's an edge, we union the node, right? And for each edge, and we union the node, we union also the subtrees that they are part of. So every time we have an edge, we union an edge, we basically get a subtree, we get a new subtree, right? We get a new subtree, and then we try to find VI. Now that makes sense. Right? We'll go some, yeah. Then we need something like this, right? So we have parent, we have rank. It doesn't really matter, honestly. What does matter is I want to know, given my current parent, I want to know how many the counts of a specific value. That's what I want to know. That's what I want to know. The count. Count. So it'll be counter. So this one, self, given a parent, we want to know the count parent which can be considered the root of a subtree, right? We want to know the number of nodes in the subtree that has a given value, right? It has a given value. Has a given value. No, it should be vowels. Oh, I'm passing another thing. So this value, account 1, right? Then find, that's just to get the parent. Union, they have to union to, because I want a smaller one to be the root. It doesn't really matter which one is the root though. No, it doesn't really matter which one is the root. So I think I'll just do the most basic union find. So this is the most basic union with the count. But when we find doesn't really matter. Union, we need to change the count. So when we union these two, that's not equal to, now we do a bunch of this, then they will be the same, right? Then I need to update the count. How do we update the count? Shall we update count for both of them? No, it's going to be, in this case, it's going to be px. You know what? Do this outside. It's not part of union find. This is union find. And then we leave as is. I delete all of this. Okay. So what do we want to do? We want a count which tells us how many counts given a parent, right? And we want to go edges from small to large. So we're going to say sorted edges equals sorted. Wait, hold on. It has a max. That's what confused me. We get a max of the two. In my mind, we should get a minimum of the two. If we get a minimum of the two, right, then every time we get the smallest value. That's not right. So what we want is when we union the two, okay, when we union the two, then we can go in and look for the maximum value. Yes, it should be the max value of the two. So when we pick any link, right? We pick any link, and it also go from small to large, right? It goes from small to large. So it would be the smallest big value between the two. So when we go small to large, we union this, right? So next one we have another 2, and then we union this, and we're trying to see if they connect to anything. No, they do not. So in this case, we have 1, 3, 1, 2. So the 2 will go out first. Because the smallest, they don't have anything. So we'll have 2, 1, and 2, 2, 1, and 2, 1. Right? So we got 2, 1, we union them. And try to find how many is that 2. Nothing, there's only 1. And the other one is 0. And then we union these two. So when we union these two, they combine. All right? And then the parent, that's also 1. No good. The next is only 3. So 3, 1 or 3, 1, doesn't matter. So we union these two. Then when we're using these two, we have to find 3. Because the previous one is all smaller than this. Because we sort that way. Right? We sort based on the larger of the two. Right? So the next pair, this must be larger than everything. Okay? And then we try to see this, how many. So we union, so we get a union. Then we need to count how many is this. Nothing. Then we have this, right? We have this subtree. And then we union. And we find this, which is this. And we find this. And then we can do, let me think one more time. So we sort from small to big, the bigger value of the two. Right? This guarantees that whenever we hit a connection, right, a link, the bigger value is going to be bigger than all the previous. Now, this thing has not been unioned into the previous one. So the previous one, we might have some union. That's okay. Some subtrees been built up. Now the new one, we're trying to union them, right? But before union them, we look for their parent. And once we look for their parent, we'll see, because at that moment, it's still two separate, right? It's not a full tree. And then we'll say its parent, how many? Like if this one doesn't connect to anything, if it does connect to anything, it will be connected, which means it has seen before, it will be connected. Then we'll find a total number in that one. So every time we'll add a new one in, and we add a new one in. Every link can merge two subtrees, right? So we just want to find one subtree and find the other subtree. So this will be max A and B. For A, B in edges. Important step. This guarantees that when a new max val AB is considered, max val is the max value of all the values that have been encountered before. Okay. Now, we also need DSU. Vowels, right? And res equals len vowels. For MV, max V, A and B in sorted edges, right? We need to first find the root of a subtree, right? Subtree that A and B belong. So we're going to say root A, root B equals DSU dot find DFS DSU dot find A DSU dot find B, right? So I'll find them, right? And then we want to see count VA, count VB, count masters in root A, count master V in root B shall equal to count root A and V, count root B max value, right? Find the number of nodes that have value MV in subtree rooted in RA and subtree rooted in RB. So now we find the count, and then we say since MV is the largest value at the moment, right? So how do we know they must be connected? Well, because A and B are connected, right? A and B are connected, so root A, yeah. And since A and B are connected, subtree RA and RB are also connected. Therefore, all the paths that connect nodes of value MV in RA and nodes of value MV in RB, all the paths count, and the number of such paths is the product of the two counts. So we say res plus equal to count this times count this, and then we union DSU dot union RARB, right? We union the two so they become together, and we update. We update the count. Union the two subtree and update the count. We just say count DSU dot find RA shall equal to counter master value count this plus count this. Note that we do not not update the count and change the count. We do not update the count, but create a new one. This is because once we encounter a new, well, actually, we don't have to. We can just add. No, we don't want to add. This is the current value, we want to add it together. I mean, what we can do is like completely update. Yeah, we can just say this is the new root. I would just say mv equals this. Okay, and then we'll return rest. This should be len vals. It's not right. Nothing wrong with DSU. I think DSU is right. Yeah, actually, I'm not sure. Let's take a look. I add one more. Parent print count. And I want to know the current. So we start with 2, 0. Okay, these two. So these two are union together. And encounter, yeah, makes sense. Five, 7. Well, what's the answer? The answer should be 6. So I do this 3. It becomes 7. 7. How is it 7? Zero and a 4. 0 and 4. 0 has 2 3s. 0 has 2 3s. Yeah, 0 has no 3s. 3 0 1. 3 0 1. Right? 0 and a 1. And this one hasn't even encountered yet. And parent RA or B. Yeah, it's a 0, 1, a 0 and a 1. How does it become 2? I don't understand. Oh, so union A and B. Still not right. Oh my god. RA. Typo. Typo. I was wrong on a typo. Jeez. Okay. Let's do this one more time. Should be 631. It's not right. The heck? What did I do wrong? Should be 10. Okay, this one's right. I don't know. We can do a counter. The thing is, I don't think this... Yeah, it's the same thing. How is mine is not correct, but his is correct. What's the difference? Oh my god. That's... I consider that a typo as well. Come on, union find typo. Okay. I will not be able to solve this at all. At all. Can solve this. The solution is from 8 to 15. All right, that'll be it. Damn. I'll see you guys tomorrow.